I am going to talk about another downstream operation, it is called adsorption. So, here you have a solid, that is called the adsorbent, and then you have either a liquid or a gas where you have the solute or the adsorbate. So, the adsorbate gets adsorbed on the solid adsorbent, and that is what is called the adsorption phenomena. Said, so the solids get accumulated onto the surface and they start moving from the bulk and get adsorbed onto the surface. So, the solute could be in the liquid form or it could be in gaseous form, and the surface phenomena is what is happening. So, we have the adsorbate, that is the material that is getting adsorbed, and we have the adsorbent which absorbs the adsorbate. So, this type of adsorbent could be like silica gel, activated carbon, zeolites. So many different types of adsorbents are available nowadays in market, and it can help. For example, if I want to decolorize certain liquids after the fermentation, I can use an adsorption process where the color material which gives the color to the solution can get adsorbed. So, you can get a very clear looking solution once we perform an adsorbent. Now, adsorption is an exothermic phenomenon. That means when you perform this particular action, there will be a small heat that is going to get liberated. So, the forces of attraction exist between the adsorbate and the adsorbent. Adsorbent is your solid, adsorbate is your solute, which could be gas or liquid, and due to this forces of attraction, heat is released. Okay. So, there are types of adsorption that can take place, and the forces of attraction involved here are like van der Waals forces, or it could be a chemical bond also, that could be a much stronger force. So, van der Waals forces or something called non-bonded interaction, they are weak forces, and the type of adsorption can be classified as physical or chemical. As you can see, the name implies very clearly, physical will not have a strong bond or permanent bond or a covalent bond formed, whereas in chemical adsorption there could be a bond formation also. So, two types of adsorption: physisorption, that is a physical adsorption; chemisorption, that is a chemical absorption. So, here you have van der Waals forces, here it could be forming chemical bonds. The enthalpy is 20 to 40 kilojoule per mole, here we are talking almost 10 times more. This is generally observed at low temperature. So, if I keep increasing temperature, physisorption is not favorable. This takes place at high temperature. This is not very specific, this is very specific. You can have multiple layers of the adsorbate formed on the adsorbent, whereas generally this is a monomolecular layer. This is a reversible process and this is a irreversible process. Okay. So, where do you use this type of adsorption? Charcoal, for example, is used for decolorizing, like I mentioned, especially you want to remove some color from liquid, then charcoal is a very good adsorbent. Silica gel can absorb moisture, so it is used in desiccator. Silica alumina gels are used for as adsorbent for controlling humidity of rooms. Activated charcoal is used in gas masks for removing toxic gases, sometimes even methane and so on actually, so that it purifies the air. It can also be used for carrying out some heterogeneous type of reaction. If I am using oxidation or hydrogenation reaction using nickel, or oxidation type of reactions, or if I am using a catalyst like platinum hydrogenation and so on, there you will come across adsorption. So, what are the factors that govern adsorption? Temperature is a very important factor. If you remember Lee Chatelier's principle, and if you assume the adsorption process like A plus S going to AS, that is the adsorbed material, A is your solute, S is your adsorbent. Okay. So, low temperature favors the forward reaction, low temperature will favor the adsorption process. Okay. Pressure, as you increase pressure, the adsorption goes up and then it will reach saturation. This is valid generally in gaseous type of adsorption, not for the liquid systems. Pressure will not play much role in the liquid systems, but for gaseous systems yes. Surface area, if you increase surface area then adsorption also increases, larger the surface area larger is the adsorption. How do you activate your adsorbent? We can break it into smaller pieces, that is you can break the crystals, we can heat it to high temperature, we can wash it with the acid. By doing all this we are increasing the activity of the adsorbent and thereby allowing it to absorb more of the adsorbate. Different types of adsorption, linear, Freundlich, Langmuir, these are the 3 types. We will look at them little bit in more detail and they are all governed by a theory called BET theory. Let us not go too much into that, but these 3 types of adsorption takes place. So, if I plot in the x axis the solute concentration in the solution, we call it x, that is concentration of the adsorbate in the solution, q in the y axis concentration of the solute in the adsorbed, that is solid phase, okay. Q is the concentration of the solute in the adsorbent, that is in the solid, x is the concentration of the solute in the solution, okay. Then you can have 3 types of relationship. If it is linearly varying like this is called a linear adsorption isotherm. So, Q will be equal to Kx, K is a constant, okay. If you remember in your extraction K, we used to have y is equal to Kx, okay, K is called the partition coefficient. So, here that is also a linear relationship. Here also when you have a linear adsorption relationship you will have Q equal to Kx. This is called Langmuir adsorption relationship. So, Q is equal to Q naught x by some capital K plus x, okay. The Q naught could be the maximum the adsorbate can adsorb on the adsorbent, maximum that can happen actually. So, that is why you call Q naught. K is a constant here. So, Q is equal to Q naught x divided by K plus x here, okay. So, the graph will go up and then reach a saturation. The third type is called the Freundlich. So, the graph will be shooting up like this, Q is equal to Kxn, okay. Generally we do not find much of this actually, generally we will find this, and if you look at this graph at lower concentrations of solute this looks like a linear, at higher concentrations of solute it is flattening out. So, generally we find a linear relation at low concentration and at higher concentration the flattening out of this relationship or isotherm it is called. So, you can see the x axis is the solute concentration in the solution and y axis is the amount of solute adsorbed per adsorbent, okay. So, the units are very different. Q will have like grams of adsorbate on grams of adsorbent, whereas in x it will be like grams of adsorbate per liter of the solution, that is how it will look like, okay. So, let us do a mass balance if there is a batch adsorption, okay. So, we have 2 streams coming in and 2 streams going out. So, we have a feed solution with the solute concentration with Xf and we have W amount of adsorbent added with concentration of solute as Qf, and then the solids go out W again. Now, it has picked up some adsorbate, so it will be Q, and your solution has lost some adsorbate, so it will be X, which will be less than Xf, and the F is the concentration, okay. So, we can do a mass balance Qf plus F into F plus so Q Xf into F plus Q of W, okay, that is the amount of solute entering from these 2 streams, Q into W plus X into F, that is the amount of solute leaving out. So, you have 2 streams through which the solute comes in, 2 streams through which the solute is going out. So, X is the concentration of the solute in the feed after some of these solute got adsorbed by the adsorbent. Okay. So, here again just like your extraction, if you are adding fresh adsorbent, like in the extraction you are adding fresh solvent. So, if you are adding fresh adsorbent, QF will be 0. So, you can have one term x of F equal to x into F by plus QW, okay. That is possible if you are adding fresh adsorbent here. Okay. So, this is the mass balance relationship for a single stage of batch adsorption. Okay. So, if you plot that equation, that is called the operating line. Okay. So, on the y axis as I said will be Q, and on the x axis you will have the x, and Q is equal to QF plus F by W into XF minus X. That is the previous equation which I have shown here. No, this equation I am just rearranging it to bring Q on the left hand side, remaining things on the right hand side. So, when you plot Q versus X, you will get a straight line going down. Okay, this is called the operating line, and the equilibrium line could be relationship between y and x. It could be y equal to kx if it is a linear adsorption, and so on actually. Okay. So, this is called the operating line, and the other one will be the equilibrium relationship. Okay. So, you can, if it is a linear, you are going to have something like this, Q equal to x, kx. If you have going to have a Langmuir, then you will have Q equal to Q naught x plus capital K in plus x. If you are going to have a Freundlich, you will have Q equal to k x raised to the power n. So, the place where these two lines cut, that will be your the x, and that will be your Q. That is, those are the concentrations of the solute in the liquid and the concentration of the solute in the solid that is leaving the stage. Okay. So, this is called the graphical method. Okay. Let us look at a small problem. This is a useful mass balance equation, because I want to calculate what should be the amount of adsorbent I should take, that is amount of solid. It could be silica gel or carbon or zeolite that I need to take. Okay. And if I want to adsorb 90% of whatever solute is entering. So, the solute is entering here at a feed concentration, okay, 0.1 mg per liter, and the F is 1.2 liters. Now, how much of W I require if I want to adsorb 90%? Okay. Now, I am using fresh adsorbent. So, QF will be 0. So, this term will be 0. So, I take the mass balance equation, okay, and I know the XF. So, 10% of XF will be what is going out, X. So, I will take the mass balance equation like XF plus into F plus QF into W is equal to XF plus X into F plus Q into W. Okay. QF is 0 because I am using fresh adsorbent. So, X is equal to XF is the feed, that is 0.1, F is my feed quantity 1.2, 90% adsorbed. So, remaining 10% is what is coming here, okay, here 0.01, and Q is equal to Kx, because I have said it is a linear adsorption equation, K is given here. So, Q equal to Kx. So, instead of Q here I can put Kx, okay, and I know the X value here. So, I calculate W, I end up with 108 grams. So, I need 108 grams to recover 90% of my adsorbate, okay, where I say it is a linear adsorption relation, I given F and I have given the W. Okay. Now, let us look at another problem. I have a feed 1.2 liters, that is F, containing so much of protein, okay, that is my XF. I am adding 80 cc of an adsorbent, okay, and I am saying it will adsorb maximum is so much moles of protein. Okay, it follows a Langmuir relationship. So, you know Langmuir relationship, right? Q is equal to Q naught x by capital K plus x. K is given here, Q naught is given here, because I am saying maximum. So, Q naught is given here, K is given here. Okay. So, simple, Q is equal to Q max x divided by K plus x. Q max is given this, and K is given here, and then I use a mass balance again, W into Q. Now, again I am using fresh adsorbent. So, my concentration of solute in the feed is in the adsorbent is 0. So, I can adjust, put them together, I can calculate, okay, what will be the concentration of the solute in the solution leaving, simple. Okay. It is quite an useful relationship using just the mass balance. Now, I can have two stages of adsorption, just like two stages of extraction. So, each time I am adding some amount of adsorbent and it is fresh adsorbent, that is why I put here QF is equal to 0, you can see this, right. So, my feed is coming here at 1 liter and the concentration of the solute is 0.1 grams per cc. So, some solute gets adsorbed. Now, same thing goes into the next one, some solute gets adsorbed. So, I want to know what is the final concentration and I want to know what is the overall efficiency of adsorption. Okay. So, first one I do a mass balance, I know the relationship and I can calculate x1, right, that is 42.8%. Okay. So, percentage of recovery is 42.8% recovery. Okay. Now, that concentration goes here and again I am adding fresh adsorbent, again I use the same mass balance equation, I calculate x2 and again I can calculate the overall efficiency of recovery. Okay. So, x2 is this, x1 is this and xf is 0.1. So, from 0.1 it goes down to 0.057, then it goes down to 0.0326. So, the overall recovery is 67%. So, as you can see, just like extraction, when I move from one stage to another, this is cross flow type, because every time I am adding fresh W, okay, fresh adsorbent, I am improving the adsorption to from 42 to 67%. Okay, now I have done something interesting. So, I do not add fresh, I add fresh only in the second adsorber and I take this and put it there, slightly complicated. So, only here I am having W fresh. So, QF is 0, but here QF is not 0, whatever it has picked up here in the second stage is coming here. Okay. So, calculations are slightly tricky. So, I use the same mass balance, but I will have two equations, then I simultaneously I will solve for Q2, okay, and Q1 and I get very interesting. So, overall x1 comes out to be 0.075, x2 comes out to be 0.043. So, overall recovery is 56%. So, I want to compare this with the previous problem. In the previous problem I am adding fresh W in both, that means totally I have added 50 cc of adsorbent and I got a recovery of 67%. But when I take the adsorbent from the second adsorber and put it back into the first, that means I am not adding fresh 25, what happens? My adsorption efficiency is 56%. So, from 67 it has come down to 56%, but I have used only 25 cc, okay, the same 25 only I am using it in the first, whereas in the previous one I have used 50 cc of adsorbent. So, you see I have reduced the adsorbent by half and I am, instead of 65 I come down to about 57. Okay. So, if the cost of the adsorbent is very high, I would have saved quite a lot of cost, okay, I would have reduced the expenses by half. So, this is very important. The previous example is almost like a cross flow, okay, cross flow where I am every time adding fresh adsorbent, but whereas in this particular example I am taking the adsorbent from the second stage, putting it into first stage. So, this is like a counter current adsorption, just like counter current extraction. In the previous class I talked about cross flow extraction, counter current extraction, same thing here, but the advantage, as you can see, is tremendous. I am able to reduce the amount of adsorbent by half, but my efficiency has gone down a little bit. So, it has come down to 57, whereas in the other case it was if I add a 25 cc fresh in each, I get about 65. Okay. So, that is the advantage of doing a counter current operation, right. Okay. Now, let us look at continuous stirred tank adsorber. So, generally your adsorbent is inside, the solids they are suspended in an agitator. So, you are adding fresh feed containing some solute XF, it gets adsorbed and then it goes out, then which will have a concentration of X. So, this is continuously it can happen until your adsorbent gets totally saturated. At that point you may have to stop the adsorption process and try to either drain everything and then add fresh adsorbent, or add some chemical which will activate your adsorbent. So, this is a continuous. Okay. So, the equations are much more complicated, you do not get scared by this. So, on the left hand side we have how the concentration of the adsorbate changes with time, dx by dt, V is the volume, E is called the voidage of the reactor, I mean sorry, of the adsorber. So, 1 minus E will be the amount of solids present, 1 minus E into V is the amount of solids present, E into V is the amount of liquid present inside the tank. F into XF is the amount of solute that is entering, F into X is the amount of solute that is leaving. Okay. XF is large, X is small because some adsorption has taken place. Okay. Then R adsorption is the rate of adsorption per volume of tank. Okay. So, you have input, you have output through the flow, and the liquid loses some solute because it gets adsorbed onto the adsorbent. So, this is the mass balance for the solute. So, R adsorption we can put different equations, we can put Langmuir adsorption, we can put Freundlich, we can put linear or whatever you feel like, right. Now, another thing that you need to consider is some sort of a mass transfer that is taking place, right, because there is a the solute has to move from the solution bulk and come to the surface of your solid adsorbent. So, there is a mass transfer KLA, KL is the mass transfer coefficient, A is the surface area of adsorbent per tank volume, X is the concentration of the solute in the bulk liquid, X star is the concentration of the solute which will be in equilibrium with the adsorbent. Okay. Now, this X star and Q are related like this, Q for a linear relation Q equal to K X star. So, I can put here instead of X star Q by K. So, there are two equations, one differential equation and one equation for R adsorption. So, we can solve it and you can end up with this type of relation as a function of time. You can see, okay, how these things change actually. Okay. So, Q divided by K XF is equal to 1 minus and so on actually. Okay. Minus sigma 1 T minus sigma 2 T, where sigma 1 2 are given like this and the B is given like this, that is B of here is given like this. So, do not get scared of this. So, what this relationship gives you is how Q varies with respect to time. This is okay, how Q varies with respect to time. K is the equilibrium constant for a linear system, XF is the amount of solute that is entering in the feed liquid, okay, and so on actually. Let us not get scared, but how will Q will build up like that, because as the adsorbent keeps taking in solute or the adsorbate as a function of time, the concentration of the solute will go up and then finally reach saturation. And if you look at the liquid side, that is XF minus X, it will keep going down and finally that also will reach saturation. So, after this there is no adsorption that is going to take place. So, I need to stop my adsorption process and then I need to replace the adsorbent with fresh adsorbent, otherwise it is of no use. So, generally by this time the adsorption process is stopped and then they have to either reactivate the adsorbent or charge with the fresh adsorbent, that is what is done actually. Okay. You can also have a tubular adsorption, that means the adsorbent is packed in a tube and the fluid containing the solute or the adsorbate is charged inside, okay, as a function of time. So, here it gets adsorbed here and product will come out here, the liquid. So, initially this is a fresh okay, fresh adsorbent. So, the every solute that is entering will get adsorbed. So, you will not see any solute or adsorbate in the fluid that is leaving, and then after some time it will start coming out and coming out. That means by the time your adsorbent is totally saturated. So, this after some time it takes off. This time is called breakthrough. This is called a breakthrough curve, because initially the adsorbent is very fresh. So, all the solute gets completely adsorbed, but as it gets saturated, after some time the adsorbent has no power to capture the solute. So, the solute that is entering starts coming out, and then finally it comes out fully. Okay. So, this is called a breakthrough curve, and this is the equation. This is a partial differential equation where we have time here, we have Z is the distance along this length, and so the concentration of the solute varies as a function of length as well as the x as well as the time. Okay. So, x is a function of time as well as x is a function of z here. So, let us not bother too much about this relation, but we will think about this breakthrough. Okay. So, if you look at the equation more in detail, this is called the accumulation term, this is due to flow, this is due to diffusion, and this is due to the transport of the solute from the liquid phase to the solid adsorbent. So, this is how the equation is broken down. Let us again not bother. So, initially the concentration of the solute coming out of the tubular adsorber will be 0, because your solute is fresh. So, it is absorbing everything, but after some time it start coming out. Okay. And then finally everything comes out. So, this is called the breakthrough time TB, and this is called TE, exhaustion time. Okay. Complete breakthrough happens here. So, this is very important, the breakthrough curve, because you have to stop your adsorption as soon as you see some solute coming out, and then you may have to recharge your tubular adsorber, either put in a fresh adsorbent or activate it by passing some chemical through it actually. So, this breakthrough curve is very important, the breakthrough time is also very important. So, there are some relationship. This portion is called the equilibrium zone and this portion is called the adsorption zone, and there are some relationship which relates equilibrium zone and the adsorption zone. So, let us not bother about how they are derived, but this is how there is a relationship. The fraction of the bed which is loaded when there is a breakthrough is given by 1 minus delta T, that means the exhaustion time minus breakthrough time divided by 2 times breakthrough time. Okay. So, the fraction of the bed is used up loaded when the breakthrough happens is 1 minus TE minus TB divided by 2 TB. Let us not bother too much how the relationship is derived. So, the adsorption zone, so this is the equilibrium zone and that is the equilibrium zone and this is the adsorption zone. Okay. I can use to calculate the equilibrium zone, I can use to calculate the fraction of the bed used for this particular problem. Okay. So, solute is coming at 1.3 mg per liter, length is so much, epsilon is so much, fluid is coming out, K is given by 38, breakthrough time is 6.4 hours, exhaustion time is 10. So, theta, this fraction of the bed is given by 1 minus 10 minus 6.4 divided by 2 times 6.4, right. So, that is what you do. Okay. This is the equilibrium time, this is absorption zone. So, fraction of the bed used 1 minus delta T by 2 TB, that is 72. So, 72% of the bed is totally consumed when the breakthrough happens. We would like to have much larger and larger, so that most of the bed is used up. Okay. Then how do you calculate the adsorption zone? As I said, this is the adsorption zone, this is the equilibrium zone. So, we can calculate from this relationship. 1.3 is the flow rate, 10 power 6 is the exhaustion time, 6 power 4 is the breakthrough time divided by 6 power 4. So, adsorption zone is 0.73. Okay. And 1.3 is the total length. So, 1.3 minus 0.73 is 0.57, which is the equilibrium zone. So, 0.757 is the equilibrium and 0.57 is the equilibrium and 0.73 is the adsorption zone. Okay. So, together it makes the 1.3 meters actually. So, the relationship for calculating adsorption zone, relationship for calculating equilibrium zone is given here actually. Okay. Okay, so okay. So, feed of 1.2 liters contains so much of solute that needs to be absorbed with 20 cc of fresh adsorbent. So, Frodley relationship Q equal to 32 x raised to the power 1 by 3. So, we can plot that will call the equilibrium line here. The operating line is your mass balance. So, wherever they cut, that will give you the x in the amount of x in the x axis, and here it will give you the q in the y axis. So, this is called the graphical method. The pressure drop also we can calculate, because if you have a packed adsorber, you are going to pump in some liquid here or a gas here, and it has to overcome this entire bed. Okay. So, the pressure drop will be sufficient to overcome the entire bed, so that the liquid or gas flows on the other side. So, the length of the bed has an effect on the pressure drop, the velocity has an effect on the pressure drop, okay, and the diameter of the tube also will have an effect on the pressure drop. So, especially when we are talking about packed bed adsorbers, we need to consider the pressure drop also, unlike the agitated adsorber or a single batch stage adsorber. So, today we talked about different types of adsorbers, batch adsorption, tubular adsorption or packed bed adsorber, and stirred tank adsorber. These the last two are continuous systems, whereas the first one batch is a batch system. Then using mass balance, I told how to calculate the various important parameters, like how much adsorbent I will require, given the amount of adsorbent, what will be the efficiency of adsorption. If I have multi-stage cross flow system, how many stages I will require. If it is a counter current system, what will be the efficiency of adsorption, and so on actually. So, just by using those mass balance equations, we are able to do all these calculations, and it is extremely powerful. And one interesting thing which we saw is there are the entire logic, the mass balance calculations, the cross flow, counter current flow, all these, they look very similar to liquid extraction. So, there are a lot of similarities. So, the partition coefficient K in liquid extraction is same as the linear K in the linear adsorption isotherm. So, we can see there are similarities between the stage operation of a liquid extraction with respect to a single stage adsorption unit operation. Thank you very much.